Hello, I'm Tim Lichtenberg from Oxford, and the research I will present here is in collaboration with Joanna Drążkowska, Maria Schönbächler, Gregor Gorlabek, and Thomas Hans. Our research is motivated by the question of how substructure that we observe in exoplanetary systems in protoplanetary disks is potentially related to the isotope dichotomy and chemical fractionation that we observe between the inner and the outer solar system. To further motivate our research, let us have a look at those plots here, which present evidence for temporal fragmentation of the planet formation process from both exoplanetary systems and from the early solar system. On the left-hand side, we see stellar mass, where this mass in solids, in either the dust component of disks or in exoplanetary cores, showing that the dust mass, the total dust mass in disks, decreases substantially from class 0 to 1 to 2. And in class 2 is not enough anymore, not sufficient, to explain the masses of exoplanetary systems. And this suggests that the dust component somehow gets incorporated potentially into larger objects relatively early during the evolution of the disk. And the planet formation process starts early. We have complementary evidence here on the right-hand side from the early solar system, from the timing of iron core formation in planetesimals or in meteorite parent bodies, showing that these planetesimals formed cores relatively early on. Because they need an initial heat-up phase, this suggests that these planetesimal families that we have eventually measured today in the forms of their cores must have formed early, potentially as early as the class 0 or 1 phase. Now, in addition to this suggestion of an early onset of planet formation, from hafnium tungsten dating, we have evidence for a protracted finish of the accretion process for Earth and Mars, showing that the proto-Earth very likely accreted several tens of millions of years longer than the proto-solar disk lived. Now, in addition to this temporal information, we have evidence about the spatial extent of planet formation and spatial substructure here shown in dust component substructure in IMA disks, and complementary evidence again from the solar system in chromium versus titanium space, showing the relatively often discussed dichotomy in neutron-rich supernova-derived isotopes, separating the NC reservoir from the CC reservoir. Now, what we aim to do in this project here is to suggest an explanation for this by building a coupled model of the disk, starting from the infall stage, and calculating, quantifying the compositional evolution of the planetesimal reservoirs that form during the infall and the class 2 disk stage. Our model here starts in the infall stage, makes use of this of the so-called inside-out rotating infall model. The protosun, this scenario, accretes from the surrounding molecular cloud, and the disk is built up from the inside out. Now, the solid material in this disk here is illustrated in this figure here. Now, material is in dust grains. Inside the snowline, the water is in the vapor phase. Outside the snowline, the water is in ice phases, and thereby the solid density is enhanced. Dust grains coagulate, and because when they grow, the aerodynamic drag with the surrounding gas from the surrounding gas becomes larger. Therefore, the drift velocity toward the protostar increases, but when they cross the water ice line, they dehydrate, their size decreases, and therefore their drift speed reduces and they drift slower. This leads to traffic jams at the location of the ice line, and this facilitates planetesimal formation by the streaming instability mechanism. This happens on roughly a timescale of 10 to the 5 years. In addition to this traffic jam effect, there's an additional mechanism called the coat-finger effect. This happens because water vapor from the inside of the snowline diffuses outward and refreezes onto grains just outside the snowline, again facilitating planetesimal formation by enhancing the solid surface density. This happens on about 10 to the 3 years, on a 10 to the 3 year timescale. Now, Joanna Drążkowska and Kees Dülman published the simulation that we make use of in this work in 2018, and I refer to this paper if you are interested in further details about these simulations, here I show a movie of the build-up of 2 consecutive planetesimal bursts that result from in this scenario. So what you see is the movement of the snowline from the infall stage to the disk stage, to the class 2 stage. You see 2 subsequently forming planetesimal reservoirs that differ in their formation times. First planetesimal reservoir forms mostly due to the cold finger effect. The second one, with a substantially enhanced mass, overall total mass, forms in the outer solar system, mostly due to the traffic jam effect. Now this has substantial implications for the internal evolution of these bodies, because the earliest planetesimals were heated from aluminum-26 decay. This plot here showing radiogenic heating in log units of watts per kilogram of silicate material for this time of the solar system formation, showing that the initial heating source of these bodies was aluminum-26. We can make computational models of this, such as this, and in this project we're interested in quantifying the compositional changes that make such compositional influence this has potentially on the deviation between the reservoir 1 in our simulations and reservoir 2 in our simulations. Now quantified, you see here the planetesimal radius and formation time of the sea ice, and you see highest mean temperature over an interval of 5 million years of evolution, showing that it gets really hot for relatively large and early formed planetesimals. We're interested especially in hydrothermal activity and core formation planetesimals. The H1 and H2 lines are associated with potential scenarios for internal compositional evolution. If you have an initial water ice rich planetesimal, then this water will melt. Eventually the hydrous rock will again decompose when it becomes very hot. And also planetesimals that become hot enough, they form cores either due to percolation or rainout. Now we derive from this scenario, the time-dependent evolution which relates to hydrothermal activity and core formation. The inner solar system, or reservoir 1 here, experiences high internal processing, whereas the reservoir 2 experiences low internal processing. Now our time-dependent evolution looks like this. This is time of the sea ice and fraction of birth planetesimal population. Reservoir 1 produces a peak of core formation at about 1 million years. Reservoir 2 produces a peak at about 3 to 4 million years. And this shows the ages of metal silicate segregation in the NC and CC record. Our reservoir 1 reproduces roughly the clustering of the ages in the NC reservoir, and reservoir 2 reproduces the clustering of the ages within the uncertainties in the CC reservoir. We perform similar exercise for aqueous alteration. Reservoir 2 here produces a peak at about 4 to 5 million years, which reproduces the clustering of aqueous alteration ages in the CC record over here. In addition to this compositional information and compositional chronology, this makes some statements, potential statements about the isotope dichotomy. Now it is important to say that the largest danger to homogenizing an initial heterogeneity in the isotope component of the dust grains is dust drift or pebble drift. Now pebbles drift inward on a timescale of potentially 1,000 years, which is much lower than the disk evolutionary timescale, and therefore this drift must somehow be stopped to some extent to observe the dichotomy we see. This is typically suggested, or in literature currently, it's mostly suggested to be the result of an early formed Jupiter core. And here we quantify our simulations and see if it can potentially explain or present a potential mechanism to initiate this dichotomy. Now we quantify the pebble flux at 2 and 15 AU. This is what you see in the bottom right here. The pebble flux at 2 AU is the red line, and the pebble flux at 15 AU, roughly representative of reservoir 1 or reservoir 2 respectively, is the blue line here. Now this is pebble flux in millions of years, in Earth masses per million year, and this is time after sea ice. What you see is that initially the pebble flux is roughly similar, but over time it substantially deviates from each other, which is because the dust mass from the outer solar system is preferentially incorporated into reservoir 2. This suggests suggests a potential explanation for the isotope dichotomy. If there's an initial heterogeneity in the isotope content of the inner and outer disk, then this will be preserved because the material is not that from the outer solar system doesn't reach the inner solar system. Now, additionally, this makes some suggestions for the growth mode. We contrast planetesimal accretion with pebble accretion. Here in the scenario shown on the bottom, it shows growth time scale, it shows time after CAIs. The solid line is pebble accretion, the dashed line is planetesimal collisional accretion, showing that the early phase in our simulation is dominated by collisional growth, then transitioning into a pebble dominated phase, then again to a pebble starved or collision dominated phase again, which is because again the pebble flux in the inner solar system is substantially decreased by up to 2 orders of magnitude toward the end phases of the disk lifetime. Now, this is a summary of our scenario, which I do not have the time to go fully into, but I'm most happy to discuss this, showing how our scenario suggests potential explanations for the isotope dichotomy that we see and the chemical fractionation, meaning volatile poor inner solar system versus volatile rich outer solar system, water accretion, and the mode of growth in the inner versus the outer solar system. Let me shortly summarize. So our model suggests explanations for the reservoir separation, and which is in our model, in our scenario, explained by protoplanet seeding itself. The inner solar system starts accreting first, but experiences pro-directed growth with a heterogeneous growth mode, starting with collisions, going to pebbles, going to collisions. The compositional and isotope dichotomy in the solar system is a result in our scenario, the spatially and temporally distinct planetesimal bursts that are built up first in the inner and then the outer solar system, and subsequent divergent geophysical evolution from radiogenic heating, which suggests a water accretion sequence starting with the water depleted material, transitioning to dry, and then to water rich material toward the end stages of accretion. Thank you very much.